a graph of to graph line, I need to have two different points. And that's the key idea. So if you have a pair of points, you connect these 2 points, one with another, and that's how you produce yourself a nice line. And that's what they're discussing here. But sometimes this may not be the case, like in exercise, say, number 13, where we actually have line which is x equal to 3 or a vertical line. So it turns out that it's good to realize that if you deal with a vertical line, its equation has only letter x, which is 3, so it looks somehow like that. And the reason this is a vertical line, you can verify by taking various pairs or points on a plane. So say you can use, for example, number 0 for y, but x is going to be 3, right? Because that's what x is. You can take 1 instead of y, and x is also going to be 3. Or you can take anything you like, let's say 5 instead of y, and x is still going to be 3. So pairs such as a 3, 0 or 3, 1 or 3, 5 are all on the same vertical line. And this is good to realize. And we're going to use these vertical lines a lot in our class. They will be called usually as vertical asymptotes. If you heard that word, if not, it's fine. Asymptotes, that's what we're gonna use to help us to graph various functions. Y is equal to 5, exercise number 14, is analogous looking equation with only one variable letter y. And this is 5, so it's gonna be passing on the y-axis through 0.5 and will be a horizontal line. Sometimes people say this is line with 0 slope. If you recall that favorite slope times x plus y-axis intercept form of the equation, whenever you deal with lines, very often they like to write equations in this form. They like to call this as a slope and y-axis intercept equation. Did you ever hear that before? Y-axis intercept. So this helpful to know to be able to graph. Like, for example, if I know that slope here is 0 and the intersection with y-axis is 5, that's what we actually can visualize from the graph, that indeed the line hits 5 on my y-axis. So it is y-axis intercept. Then slope 0 means the line is horizontal. So it's not going up or down. It's just the horizontal line. The point is that equations of vertical and horizontal line have analogous equations. They have either x is 3 or y equals to 3. And in general, equations of lines, they all have analogous structure with some numbers around just x and y. So for example, if somebody looks at exercise 20, that may seem to be a kind of unusual looking equation. Well, they want you to write it in a form which is slope and intercept, so you can definitely do a little bit of algebra here by making those denominators to go away, right? So what I can do is take this 5 and -2, actually -5 and +2, and to rid of those denominators, I can multiply them and get 10. So I can multiply by -10 each piece of my equation, because this will enable me to lose those denominators, just like that. Just cancel these and get -2 here. Cancel that and get -5. So when I distribute this, -2 will get -2x and -6. And then next we'll be multiplying -5 by y, and then by -2, so it'll be +10. And on the other side, it's a -10. Please notice that if you don't like to work with fractions, then you can just make them disappear right away. And then what? Well, this is my goal. Y is on one side, so I want to bring everything else to the other side of my equation. So I'm going to change their signs. So I keep -10 the way it is, and then I bring -2x as a +2x to the right. I bring the -6 as +6 to the right. And then -5y will stay, so it's -10 that comes over. So this is what I'm going to get now. And then we have a -5y, which is equal to 2x, and then there's a bunch of numbers. So you have -10 is -20, and then 6 is -14, right? So looks like it's a little bit better, just -5 needs to go away. So we're going to divide by -5 each entry of this equation. So I get a y on one side, and this will be equal to -2/5 with x. And then we also have positive when I divide 14 by 5, positive 14/5. So here's the answer, and we're done. It looks like this is the way to do problems in here. So it looks like we're now going to see what else is here. What else is not from all of the exercises, but just from those problems we need. My goal for this exercise was just to, well, make sure that you be able to see how we clear those denominators. So I'm going to move to the next section, because I think that 1.3 is pretty much all I need is those vertical and horizontal lines for the calculus purposes. And next section deals again with functions. And I think this section is something that I may not need to worry much about, because this is really a word problem section that I don't think we're really gonna utilize much in this class. That's why I'm gonna simply skip it. Skip means don't worry about it. So just disregard this little story and move right into finding so-called limits. And that's what I wanna not to hurry with, because that's where the calculus starts. So what's the idea of limit? Well, for example, you can take a look at picture part B here, and we'll be looking for the limit of this function. So we say limit, and we usually call as a function with some kind of letter, let's say function f of x, so I can see what kind of limit we're looking for, limit of this function. And when x is approaching to number 2, so it looks like the key picture here will be observing what happens with x when it approaches to number 2. So if it just keeps getting closer and closer and closer to 2, I say, so what? It gets closer to 2. Well, what I care is about function. I care about y coordinates. I care about values of function. Where are they going? I say, Alex, looks like they keep going and going and going. They're going upwards. So they're going all the way to infinity. So the limit of this function is going to be infinity because we have the graph that goes all the way up. There is another important observation here, is that we may approach to this tool from the other side. And it could be also getting closer and closer. The y coordinates of this point also getting closer and closer to infinity. So no matter if you approach to number 2 from the right side or from the left side, our y coordinates all go to infinity. So this is how it works. So we have either side, when x goes closer to 2, our y coordinates are going to infinity. Just like that. So that's the way to go. Well, how about if I try more exercises here, and I will just go to the actual exercise set at the end of this section and going to start to get used to this idea of what happens with my function when something happens with value of x. So how about if I try exercise number 7, where we have a limit of function to find, the limit of this 3x squared minus 5x and plus 2 when x approaches to number 2. So what happens here? Well, what happens is you just need to replace the x with that number 2 and see what is going on. So I'm going to put, instead of x squared, 2 squared. Instead of 5 times x, it will be 5 times 2. And calculate. So 3 times 4 is 12. And then 5 times 2 is 10. And then plus 2. So we're going to have 4, right? So it turns out that first way to calculate limit is going to be plug the number in. And that what happens when your function is so-called continuous. In other words, here we have a parabola function, right? And this parabola function tells us the following. So when x approaches to 2, so someplace here is 2, so here's our function, then y coordinate will get closer to 4. So how do we think of this? Well, if you start to get closer to 2, so say from this direction, get closer and closer to 2, what happens with y coordinates? Well, these points are climbing down the parabola and eventually hit 4 when you get exactly 2. And that's what I did. I right away put 2 inside the function and I was able to get the result. They say, oh, so that's just plugging things in? Exactly. Yes, but the limits are not designed for that. Limits are actually designed to identify some issues with graphs. Like, for example, here we have issue at the point A. The issue is that the function keeps going up higher and higher on one side, but on the other side, it doesn't. It just stays on the same level. It stays at B. So that's the issue. The issue is break. The issue is point where a function is not continuous. That's the problem that limits are designed for. Because if there is no problem, like in the last picture here, if function is continuous, there is no point to use limit because at every point of x, there is some value y, and that value y is a second coordinate of our point on a function, and that's really all the limit shows us. So there is no point to use limit. Limits needed when function has some problems with its graph, and that's the idea. So it looks like in all exercises here that start at 7 and continue in the first column up to exercise number 14, there are no issues because these functions are not going to have any problems if you plug in the numbers. Let's say if I try exercise number 13 with finding the limit that says x approaches to 1/3 for the fraction with x plus 1 on the top and x plus 2 on the bottom, then all you have to do is plug 1/3 instead of x. So you take your function and plug in that number 1/3. And this is it, that's your limit. So the reason is you can plug this in. So how can I simplify that? Well, I guess the fastest way to deal with these fractions is to see what bothers you the most. It looks like this is denominator, right? This denominator is what I don't want to have here. So in order to make denominator to go away, I'm going to multiply by this 3 and the top and the bottom. Because technically you could just cancel this 3 and 3 and nothing done with function, but multiplying by 3, I also have to multiply the other part, and it cancels my denominators. That's why I do this. So let's see what is gonna be for the answer now. I'm gonna be writing whatever's left. So 1 left from first piece, and then it's plus 3 here, right? And then also 1 plus 2 times 3 is 6. So it's 4 divided by 7, and that's our limit. So plugging in the number is going to be the way to go. What if I try another fractional exercise, let's say exercise number 17? If I try to plug into 17 number 1, if I get 1 squared minus 1 divided by 1 minus 1, what we're going to get a 0 on the bottom and 0 on the top. And that's something that is called undetermined form. That's something that we need to work with a little bit more algebraically. Simply because once you tried to plug this number 1 instead of x, it just didn't work. So what I need is to try to notice that 0 divided by 0 could be any number. For example, it could be 1. You say, you sure? Well, what if I try to divide 6 by 3? How do I know it's 2? Because if I multiply 3, my divisor, by the result by 2, I get 6, right? So same here. You can multiply these two numbers together because you can multiply 0 by 1 and it's going to be 0. So it will give you this number. So you really? I didn't know I could divide by 0. Well, 0 divided by 0 can be any number. It could also be 2, because if you multiply 0 by 2, it is also 0. Let's see, so 0 divided by 0 is 2? No, it doesn't have to be 2, but it could be. So in order to decide on exercise number 17, turns out, I need to see what happens with this fraction when x goes to exactly number 1, right? And that's where the problem is, that we have number 1 here. And what I can do is factor my numerator with x minus 1 and with x plus 1. Because this way, x minus 1 will disappear, and all I have to find a limit of will be x plus 1. You see what happens? Limit I find of x that approaches to number 1, and since my x approaches to 1, I just plug 1 in and I see it's 2. How would you like that? It's not 1, it's 2 for this particular exercise. See what happens? If you have undeterminate form, after you plug the numbers in, if something that you can't calculate because it's actually 0 over 0, it is not defined. So we need to work algebraically on that expression, and we produce a perfectly nice answer. We produce number 2 after we cancel. How about that? Let me try number 18, one more here of the same kind. So in the exercise number 18, where you look for the limit when you have 9 minus x squared on the top. And on the bottom of this fraction is x minus 3. And when x approaches to 3, looks like I get again 0 divided by 0, because it'd be 9 minus 3 squared on the top, and 3 minus 3 on the bottom. So 0 is my denominator, and 0 is my numerator. It's not determinant, it's again 0 over 0, so I have to keep working on this. So we get a numerator to factor, and I can factor it with 3 minus x multiplied by 3 plus x. So I have this kind of undeterminate form, and the question is, can I cancel this 3 minus x and x minus 3? And the answer is yes, I can commute x minus 3, put it as 3 minus x, if I take the -1 out. Did you know that? Well, check it out. If you have a difference, when you multiply -1 by +3, it's -3 here. And if you multiply -1 by -x, it's +x. So instead of my denominator, I can actually have -1 times 3 minus x. And the reason I want to factor it like that is because we cancel this 3 minus x's. You see? So that's interesting to realize, right? You can commute numbers if there is a difference. So on the bottom, you're going to have just -1. So just one number on the bottom. And 3 plus x is what's left on the top. And now I can take the limit, because now when I replace my letter x with number 3, I'm going to still have -1 on the denominator, but 3 plus 3, or 6 in numerator, right? So when I divide the 6 by -1, I get -6. -6 is the answer. So whenever you have this undeterminate form, it means that you need to do a little bit more algebra to determine it. Because sometimes you don't have undeterminate form, even if you have a fraction. For example, let me try the same exact fraction in exercise 18, but make x approach not to 3, but to something else. Like, let's say if I have same limit, 9 minus x squared over x minus 3, but instead of 3, let's say x approaches to number 2. See, instead of 3, I decided to put 2. I just made up an exercise to show you that the only problem is at 3, because if you plug 2 instead of x, there'll be no problem here at all. Look at this. My numerator will be 9 minus 4, right, which is 5. So you just plug in numbers. And denominator is -1, 2 minus 3. So the answer is -5. And this is just fine. So we have no problem with this fraction. So the point of story, you always plug the number in and see. If it's a 0 over 0, well, then you have a problem. If it's not, well, then you have the answer. And if it happens to be a 0 over 0, if it happens to be a problem, well, then you just need to do a little bit algebra. Let me try one more, 23. This is interesting, right? So we do some new kind of exercises, but it's not really new. It's same old stuff. You already know how to factor and how to cancel. Because again, if I tried -2 into this fraction, so I'll get a -2 to the power of 2 minus -2 and -6 in numerator, and denominator will be a -2 to the power of 2, and also plus 3 multiplied by -2, and then plus 2. Then I have what? 4, right? Minus and minus is plus 2, and -6. Looks like that's 0. And then again, 4 minus 6 and plus 2. Oh, 0 over 0. So it looks like we have undeterminate form. So I need to factor. I need to factor my numerator with 2 parentheses and my denominator. Please notice it's a little bit easier to factor denominator because you don't have many choices. X squared on the bottom, factor with x, and then the last term here, plus 2. You factor it plus 2 times plus 1. There is no other way you can factor this, right? So which factor should I try here? I think I'll try x plus 2. If it doesn't work, I'll try x plus 1. So I need to factor 6, and that's a -6. So it has to be -3, right? Multiplied by x, right? Remember how it goes? Outside is -3x, and the inside product is 2x, right? So when you put them together, when you subtract from -3, +2, you get a -1. That's exactly what we have. And this enables me to cancel, and that's just what I need, because now I have a limit when x is sent to -2, and this is a x -3 in numerator, and x plus 1 in denominator. So I can try to put, instead of x, number -2, so it'd be -2 -3 and -2 plus 1. See, once you canceled, you plug that number in, whatever x is approaching to. And get yourself a nice answer. So it's -5 over -1, which is just 5. Just like that. So it looks like that's the way to find limits. We basically plug numbers in. And it's very nice when you don't need to simplify anything, but if it happens that you have to simplify, then Well, then simplify and then plug numbers in. Because the problem is a 0 divided by 0, and this is not what we can deal with. We need to make it go away. So let me try one more exercise, and then you can try. Let me try number 10, and then you can try number 9, which is going to be, I think, very nice exercise. Let me do 10 first. So we have a limit when x approaches to minus 1/2, right? So it's 1 minus 5x raised to the power of 3, I believe, right? Okay, minus 5x cubed. So I go ahead and replace my letter x with that minus 1/2. Just plug it in and then see what will come out. So I multiply minus 5 by, it's still going to be negative, and 1 cube is 1 and 2 cube is 8, isn't it? So actually subtract from 1, negative 5/8. Two minuses, they give us plus. So how do you add them? Well, 5 and 1 and 5/8 is 1 and 5/8. That's the limit. You just plug numbers in. That's always the first step. So how about you try to do one? As I recommended, I think for a quiz will be a good question, exercise number 9. So please do not hurry. This is a first calculus exercise you actually do. You find a limit for this little quiz. And as usual, all I need is your answer. So please tell me what this limit is when x approaches to 0. So you just want to take that 0, right, and plug it in, basically. And that's all we care about. And as usual, just put your answer in the chat and you'll be done for today. How about that? But please don't hurry. Make sure you carefully put the number in. I'm going to stop to record.